All right, so it's going to be linear independence and non-singular matrices. Kind of a precursor to what's going to be pretty much the foundation of what we're going to be doing going forward in the next couple chapters. So, but first, what does linear independence mean when it comes to matrices? Okay, so here's our first major definition. So, given a matrix A in its column format, column breakdown, and the equation AX equals B, right? So, a vector X and vector B. That means B can be rewritten as this. So this was called a linear combination, where the vector x itself, right, as x1, x2, x3, it's times each individual a sub n value gives you B. Okay. So that's what that represents itself. Okay. One key note here that I have is actually pretty important going forward, trying to put everything together, is the equation ax equals b is consistent, meaning it has an actual solution if and only if B is a linear combination of the columns of A. And that's a key thing. So if you can actually find a solution, that's consistent, meaning it's linear independent, or linear combination of itself. We'll talk about independence in a little bit, linear combination of it. Okay. So the question is, how do we do that? Or how do we show we can make a linear combination of this matrix? So given the vectors a1 through a3 and b, express b as a linear combination of the vectors. Now, technically, it's going to be like this, is what our goal is. Right, as we follow this format here, where this is going to be obviously vector b, and each one represents itself of a, b, c. Okay. Now, what we got to figure out is, what are these values? Okay. And again, like everything else, that means just solving for the actual matrix. Sorry, got a brain fart there. So solving for the matrix. So that just means just break it down to matrix format. So it's just going to be AX equals B. So just rewriting this now into its proper matrix format. And these equal to 3, 8, and 1. And I'll just go solving for the matrix, right? So this time I'll put these together. I'll keep the bottom one the same. So this gives you 0. This and this gives you 2. This and this gives you 4. And it also gives you 4. Okay. So I'll multiply this by 2 and add it to row 2. Keep everything else the same. Okay. All right, so make life a little easier. I'll divide this by 5. So it looks kind of manageable now. Okay, so one row pretty much down. I can move stuff around, but we pretty much got this column down. So I'll work on this column now here. So let's see. So I use these two. So multiply this by -2. And I'll put it to the top now as well. And I'll keep this one the same, so I'll bring it down here. And it looks like we found one solution. So it's going to be if and many solutions scenario. Okay. All right, so one more step just to get rid of, make it simplify a little bit more before we actually get to the process of it. So we can just do this portion here, and eventually we'll just get this. So now if I convert this, it'll be x1 minus x3 equals 1, and x2 plus 2x3 equals 2. So if we solve for x1 and x2, we get that. Okay. So since we want a linear combination, the general one would be just plug this into here, that into there, and just have an arbitrary x3. But if, let's say, we want an actual solution, we could just pick, so let's say, I don't want to be 1 because I'll give you 0. So let's say this is 3. Oh, let's say 2. 2 is not going to give you 0. So let's say 2. So that means if x3 is equal to 2, x1 is going to be negative 1, and x2 is going to be, this is 4, so minus 2. So if I go back over here and just rewrite everything, so x1 will be negative 1, so it'll be negative 1. Oh, wait. Oops. This will be plus. So this is going to be 3. Whoops, my mistake. That's 3. Let's see, this is subtracted, so that's negative. That works, okay. So x1 is going to be 3, so it'll be 3a1 minus 2a2 plus 2a3 equals b. And there we go. So that's how we do linear combinations of vector, or how to find a linear, or express it as a linear combination of matrix A. Okay. So as we go forward, find out what a zero vector is. It's pretty straightforward. Zero vector is basically just a bunch of zeros. But it's special because we have a notation for it. It's kind of like the theta. It's just a 0, either with a slash like this, or like that. Most people use it this way because this looks like a theta, and we don't want to define the theta be that way. So most of the time you see it as literally just a slash between it to incorporate these, or like the theta itself is not the same as like the angle. Okay. But what we can do now is, because we have this zero vector, we can rewrite homogeneous equations to look like this, right? Because homogeneous equations always equal 0, which means we go to our very special definition down here. So the set m dimensional vectors is said to be linear independent, which is a key thing going forward now. So these vectors are called linear independent if the only solution to the vectoric equation, so we have a homogeneous equation basically, right? So we have, as of now, we'll just talk about homogeneous equations. So it's linear independent if we have something called, remember, the trivial solution, or they all equal 0. So all these a1s or these x1s just equal 0. The set of vectors is said to be linear dependent if it's not linear independent, meaning we get another solution besides that. That's pretty much what it's saying. So if we find any one that's arbitrary for the other, like for example here, this will not be called linear independent because we don't actually get 0, 0, 0 as a solution. Okay. All right, so why don't we try examples out so you can see how you could follow and show linear independency. So determine whether the set of vectors v1 through v3 is linear independent or not. These two here. So again, all we're just going to do is just solve it and see, do we get 0, 0, 0. Okay. And again, we just keep going this process, right? So let's see. Multiply this by -2. Okay. Oh, that's nice. I could get rid of that right now. So yeah, let's do that. So that gives me 3, 0, 0, and 0. So it looks like we just got one already. So bringing this up, you just divide by 3, and I'll just bring everything down. So I'll put this one in the middle, and this one on the bottom. Okay, so multiply by -1, and add it to the third row. Gives us that now. Okay, and then trying to get rid of this stuff here. So I don't want to deal with fractions. I know I'm doing this the long way, but eventually we could do this. So multiply this by 2, multiply this by 5. And I'll keep the middle row the same, just for fun. And there we go. And again, eventually, multiplying this by 2 and adding it gives us exactly what we want. And then just dividing this by -5 gives us our 1, 1, 1. So we know that x1 all the way to x3 equal 0. So this will be a yes. So these vectors are linear independent of each other. And as you can see, you can kind of stop somewhere at some point. You don't have to go through the whole process. Like for example here, you know you can cancel that off. You don't have to do the initial step, but it's good practice just for solving for matrices. So let's try this one. So I'll do the same thing. Oh, put my zeros here. There we go. Okay, I'll keep the first one the same. Okay, that gives you 0, 5, -3, and 0. All right, multiply this by -3. And add it to the bottom one. And you kind of have the same situation we had earlier, right? So eventually this will go away, but I'll do one more step to go further. All right, let's see, what can we get rid of? I guess we'll get rid of this one here. So multiply this by 5, and multiply this by 2. Oh, I guess I have to change this. That's fine, because that's going to give me the 1 again. I guess I should have just done here. That's fine, I already did the work. All right, so now I just could do this part. And I'll keep this one constant. And we got this. And as you can tell, if I go further, if I add these two, that gets rid of that. This now becomes a 1. And again, multiply this by positive 3, gets rid of it. So this is also a yes, because eventually we'll get the same result. So it works. So on that note, since we're talking about more linear independency and how do we collaborate from one section to the other section, we have a nice interesting theorem that helps us out instead of having to do all this work. Well, some of it. So we have p vectors be a set in Rn. So what this is saying is p does not equal n. So we have some dimension like R5, R6, and some p vectors like 4, 5, 6 vectors. In this case, like 3 vectors here. Right? If p is greater than m, meaning the number of vectors we have here is higher than the dimension itself, then automatically the vectors are linear dependent on each other, meaning we don't even have to go through this process. Okay? So, for example, given the vectors in R2, show they are linear dependent. Well, the best thing about this theorem is, well, we have 3 vectors, so p is equal to 3, and our dimension is 2. Well, since 3 is greater than 2, automatically is linear dependent. Now, however, if an example asked or a question asked, prove the theorem as with this example, you would just go through this process here. So you would just put them together, and show you don't get 0, 0, 0 for x1, x2, and x3. But the theorem kind of nicely breaks it down. But again, if you were asked to show that through based off a theorem, then you would just have to go through the process, which isn't hard. You can kind of tell to do so. All right. Fun little definitions and theorems here. So if we have an n by n matrix A, is something called non-singular. So it's a square matrix. So any square matrix is called a non-singular if the only solution to our homogeneous equation is the x's are 0. If there's another solution, then A is called singular. So we have a lot of stuff happening, right? So non-singular basically is the same thing as linear independent. Right? So if it's linear independent, we automatically know it's non-singular. We'll actually have a theorem based off that. But for now, that's a nice little connection to one or the other. And we have this one here. So we have an n by n matrix A is non-singular if and only if linear independent. That was right here. Okay. So that's kind of nice. So if you have one, you automatically have the other. Okay. So let's just show how matrices are either singular or not. So to show if something's non-singular means to show it's linear independent. So we do the same thing we've done so far. Let's see if we get 0, 0. Okay, so multiply this by -2. And it looks like we're going to get it, right? Just if I make this easier for myself. Multiply this by -3 and then add it to it. We do get what we want. So this will be non-singular. Hence meaning it's linear independent. Now we'll do the next one. Same thing, multiply this by -2. And eventually we also get the same thing. Multiply this by -4 and add it, and we get our beautiful identity matrix. So this is also a yes, so this is also non-singular. Okay. And then we finish up this part by a very interesting theorem down here. So it's let A be an n by n matrix, so still square matrix. The equation Ax equals B has a unique solution for every n by 1 column matrix B if and only if A is non-singular. That's a key thing. And again, with the unique solution, meaning there's only one, right? So it's not infinite many solutions. It's a nice unique one.